Hello, my name is Thomas Yore, and for my final project in EMA 4003, I will be doing an application of diffusion. Starting off, I'd like to introduce diffusion and explain some of the concepts that we learned in class. Diffusion is mass transport by atomic motion. It is a consequence of the constant thermal motion of atoms, molecules, and particles that results in material moving from areas of high to low concentration. There are two types of diffusion: interdiffusion and self-diffusion. Interdiffusion is when atoms tend to migrate from regions of high concentration to regions of low concentration. Self-diffusion is when atoms migrate in a solid. Now, I'm going to quantify diffusion. As we can see in the flux equation here, diffusion can be defined by flux. And flux is defined as moles or mass diffusing over a certain surface area over a certain amount of time. In order to properly quantify diffusion using variables, we use Fick's first law, diffusion, which we can see here is J equals negative D times dC over dx. If the change in concentration over the change in a certain distance is linear, we can simplify dC over dx to be equal to C2 minus C1 over x2 minus x1, which can be very nice whenever we're trying to solve a problem dealing with diffusion. Also notating that D in this equation is the diffusion coefficient. Now, in order to apply diffusion, I will be answering a question from Transport Phenomena 1 using concepts learned from this class that I will also build upon. Now, the problem statement is, what is net evaporation rate? That is a typo. You can blame Dr. Toomey for that. But what is the net evaporation rate in grams per hour for a 1 centimeter diameter water droplet at 75 degrees Fahrenheit and 180 cm? And the diffusion coefficient of water in air at this temperature and pressure is 0.282 centimeters cubed per second. Answer in terms of grams per hour. So the goal of this problem is to find the amount of the liquid phase that is diffusing into the vapor phase per hour. And as we can see here, this is an example of interdiffusion. The equation that we'll start with is Fick's first law, but it will be in a slightly different form. As we can see here, J equals negative D times the total concentration of the water in the droplet times dy over dr. Here we have a water droplet evaporating, where at the edge of the water droplet, it is assumed to be completely liquid. We will use X to denote liquid mole fraction and Y for vapor mole fractions. That is just one of the assumptions that we will have to use in order to make this problem doable and less difficult. Now, for more assumptions, in order to make it easier, we have to say that the amount of liquid in the vapor phase is dilute. This simplifies the equation below. We also assume that none of the evaporated liquid going to the vapor phase is going back into the liquid phase. And also, in order to solve this problem, we will need to be given a mole fraction profile showing how the vapor mole fraction depends on the distance from the droplet. And for this problem, it is not linear. Mole fraction profile is not linear. It is defined as y equals C1 prime over R plus C2, where C1 prime equals negative C1 divided by D times the total concentration. And R is the distance from the center of the droplet to some radial distance. Now, in order to find the concentration or find the C1s and C2s, we'll have to use boundary conditions. C1 and C2 are both constants of integration. In order to find them, we will use the boundary conditions that I mentioned. So for the first boundary condition, at the edge of the liquid droplet, the radial distance is equal to the radius. It is assumed the radius of the water droplet. It is assumed that x equals 1. So using Raoult's law, we can find an expression for y at that point. Here we have Raoult's law, and when x equals 1, we can find the vapor fraction of water to be Psat over P, where Psat is the saturation pressure of water at that temperature. For the second boundary condition, we will say that when we are an infinite distance from the water droplet, where r equals infinity, y equals 0. So when applying this to our molar profile, we see that C2 equals 0. And it makes sense that the molar fraction of water in the vapor phase is 0 at that point, because when we're an infinite distance away, there's not going to be any water in general that far away diffusing. So knowing that C2 equals 0, we can now apply the first boundary condition to find that C1 prime equals P sat R times R divided by P. After applying our two boundary conditions, we find that the mole fraction profile is Y equals P sat times R divided by P and R, where R is the radial distance and R is the radius of the liquid water droplet. Now we have enough information to derive our final equation for finding the net evaporation rate of water, going from the liquid to the vapor phase. Now that we have our molar profile, we can plug this into Fick's first law to find our equation for molar flux, as shown here. In order to find the net evaporation rate, first we must multiply the flux by the cross-sectional area of the evaporation. And by cross-sectional area, I mean the area that the liquid water is diffusing across. And in this case, the water liquid is diffusing across the whole water droplet. So in order to use the correct cross-sectional area, we'll have to use the surface area of the water droplet, which is A equals 4 pi r squared. And as said in the problem statement, we're trying to find the net evaporation rate at the edge of the water droplet. Therefore, the radial distance is equal to the radius of the water droplet. Also, in order to find the total concentration, we have to use the ideal gas law, as shown here, where the molecular weight is where MW is the molecular weight of the water. Then multiplying by the cross-sectional area, and plugging in the radius of the droplet for the distance, we get the equation shown here, where N dot is the net evaporation rate of water. And also where RID is the ideal gas constant. Now we can start to get some results. So from the problem statement, we know our diffusion coefficient, we know our radius, we know our temperature, and we know our pressure. So the only two things left is to get our molecular weight and our saturation pressure. And we can use engineering toolbox to find the saturation pressure of water at the temperature, which is Psat equals 0.43 psi. Also, we know that the molecular weight of water is 18.015328 grams per mole. Now we have all the information we need to solve the problem, so all that's left is plugging in with the correct units. And when we do that, we get a value of 0.14 grams per hour. And when thinking about this value we get, it makes sense because not that much water should evaporate, because diffusion down to concentration gradient is a slow process, as we have learned in this class. Now, the final part of my project, I will be showing an animation of water diffusing from a liquid droplet into the air surrounding it. So I will show that now. So as we can see here, we have the water diffusing into the area around it. And when thinking about our second boundary condition we use, where R is an infinite distance away, we can see that from this animation, it visualizes that as it goes a distance away, the whole water completely evaporates and the concentration is 0. So this is my animation, and this was the last part of my project. So thank you for listening, and have a good day.